This podcast is brought to you by LMU Munich.
Hello everybody. So let me start by a reminder of what we did in the last part of the last lecture, because I was going a little bit too fast. So I will do a little bit of a reminder, and if anybody has questions on the previous lecture, it would be a good time to ask them. So you remember that we were considering a Hilbert space that was divided into two, and this was the black hole and the radiation, and this had, I think I call the n states. So and am I writing big enough? Can you see, Gabriel? It's okay. So tell me if I. And then we did a little calculation, and we found that we were interested in the radiation density matrix, the reduced density matrix for the radiation, and we found that the answer was very simple. The purity of the radiation density matrix was this e to the SBH plus e to the SRAD divided by e to the SBH, e to the SRAD. Okay, so this is the result that we arrived, and you remember we calculated using averages over random vectors. And in this case, so we know that the entropy of the radiation, or the logarithm of the size of the Hilbert space of the radiation, goes like n rad, where this is the average number of emitted particles. Okay. And SBH is approximately SBH of 0, so the total size of the Hilbert space, minus the average number of the. So you see that in this case we're considering a case where the black hole is getting smaller and the radiation is getting bigger, as we would expect in the case of a physically evaporating black hole. Okay? And then we defined the page time. I use n rather than t, but you can convert, since the black hole is emitting as a black body, it is emitting energy at a fixed rate, roughly, right? And each particle is emitted with, on average, a energy equal to the Hawking temperature, so I can convert the number and time and vice versa. And if the words that I said now are too abstract for you, just do the calculation. Calculate what is the average number of emitted Hawking particles as a function of time, and then you can convert from number of particles to time and vice versa. Is it okay? You look a little puzzled. It's fine. It's clear enough. Fine. Good. So n page is such that SBH of n page is equal to SRAD of n page. So if in terms of numbers, it's the midpoint of evaporation when the two systems are of the same size. This is the definition of the page time. And in this case, we can compute H2, right, the Ramy entropy of the radiation, and we find that it is approximately n rad. And this means that the state of the radiation at the page time is roughly thermal. Okay, so at that point, even though our model is a model of unitary evolution, because we are only looking at part of the system, and that part is not large enough, we have the impression that what we measure contains no information, is thermal. Okay? Now, this is not inconsistent with the rules of quantum mechanics or unitary evolution. It's just a measure of how much we know about the system. Good. So in this case, we can see that if n rad is less than n page, this is a little calculation that we did already last time, but let me repeat it. Then P rad is, right, in this case, S rad is exponentially smaller than SBH, so P rad is e to the minus S rad. And in n rad is bigger than n page, then P rad is e to the minus SBH. So this is e to the minus SBH of 0 minus n rad. So from this time on, the purity of the radiation starts to increase. And we can also calculate the information in the radiation. You remember information was the thermal entropy minus H2 rad. Okay, so in this case, it is approximately 0 for n rad less than n page, and n rad minus SBH plus n rad, so 2 n rad minus SBH of 0 for n rad larger than n page. Right? Very simple calculation. And now we can draw the graph that we drew the other time. So this is the page curve. This is so I'm drawing now first the entropy, right? So n rad, so it's a linear, here is n page, the midpoint. This is SBH of 0. So this is SBH of 0 divided by 2. And I have a graph that goes up to SBH of 0 over 2, and then goes down linearly. Okay, is this, you see that this is the graph. This sharp transition is really not singular. It's a smooth transition, but it goes from exponentially fast, right? Because here this transition occurs when these two exponents are of the same size, and this happens only for a few units of n. And if we draw the information, it is 0 here. So this page time is really the time that the first bit of information starts to come out. And then it goes up to I equal SBH of 0, right? Because it goes to, it is equal to 2n rad minus SBH. So when n rad is equal to SBH of 0, this value is SBH of 0. So in this case, we recover all the information that was there. The purity of the system, of the radiation is 1, and everything is fine. You see here that here the information starts to come out at essentially a unit rate. And this was in fact verified by a very nice calculation and thought experiment by Hayden and Preskill. They said the following. Suppose that I have a black hole that is old. This means after the page time. Then we know that the information comes out fast with every Hawking photon that is radiated. So let's do this. Let's throw a system of k bits into the black hole and see how fast we can recover the information. And it turns out that in this case, after k photons that were emitted, you can recover that information. So the black holes after the page time, they behave completely different from what you expect a black hole to behave. You expect that when you throw something into the black hole, nothing comes out. It comes out extremely scrambled. But after the page time, because of this behavior, it actually comes out essentially untouched. It's like an information mirror. Of course, you have to, in practice, you have to measure the phases and amplitude of all the outgoing Hawking photons to do that. But that is, this is the meaning, the significance of this fast rate of information release. Very good. So now I can give problem 3. So problem 3 is actually repeat the original Page calculation. Page didn't do the calculation that we did. He did a numerical simulation of this type of system and found out numerically this curve. And the problem 3 is essentially repeat the way that you can do it is using Mathematica or any other problem. You should generate a random unitary matrix. The columns or the rows of that unitary matrix are the V's that we were, the random vectors of unit size that we were using. And then you can calculate the H2 or S, the average over many random vectors. And then you should get this graph as a function of the size of the unitary matrix, right? Okay. Very well. So with that, we're basically done with the reminder of the previous lectures, and we are ready to move to the firewall problem. So if somebody has questions about this, it's a good time to ask. No questions? So let's continue. So we move to the firewall problem. Okay, so in this case, what we do so far, you remember that in the page type modeling, we didn't have some explicit dynamics. We just use some type of quantum information considerations about density matrix and so on. And now, what we would like to do is to combine this approach, the page model, with some dynamics that we want to borrow from the Hawking model that we recognize, that we went over in the first lecture. Okay, so we want to combine the Hawking model with this type of assumption that unitarity is preserved and see what happens. And so we take essentially Page plus Hawking, but in this case we need to use the so-called per production picture, and I will need to explain that. You remember that we were considering the collapsing shell, and we had the P's were the outgoing particles, and the Q's were the ingoing particles, and they were, these came from the expansion of the scalar field. this expansion of the scalar field, right? This we discussed in the first lecture. And all that we discussed in the first lecture were the outgoing particles, the P's, right? We didn't discuss the Q's because the Q's were irrelevant to finding out the properties of the outgoing radiation at plus infinity. So we could leave the Q's alone and not consider them. But now we are interested in the state of the radiation near the horizon, because the firewall problem actually will say that that state has to be a highly excited state if we continue to use the same logic. And so we need to understand how to describe the Q's in the so-called pair production picture. Okay, so what I would like to do is explain now a little bit about the Q's, and then we will be able to go back to the firewall problem and describe it. Very good. So I'll do it here. So what Hawking said is that we can view. Right. Before that, we looked at the outgoing radiation. By just saying that we have a complete set of states, we can change the basis, look at these P's and Q's, and there was this was, if you wish, just a statement about the completeness of a basis in the Hilbert space. But we didn't have a specific dynamical vision of what is going on, how these particles are emitted by the collapsing shell. And the dynamical picture is actually a picture of pair production. So let me remind you about the Schwinger effect. I'm sure that you heard about it, but maybe you don't remember it very well. And so the Schwinger effect is a pair production of charged particles in an electric field, constant electric field. Okay, in this case, let's. Okay, and the idea is very simple. We think about the pairs, let's say electron, as two levels. One is a negative energy particle, a hole, and a positive energy particle. Okay? And this, now we have an electric field E in some region of space, constant electric field E. And then we ask, or Schwinger is asking, when would this electric field start to create electron-positron pairs? Okay, so what he did, he compared the energy. He actually did a more complicated calculation, but this is a heuristic way of representing his results. So In this case, the energy stored in the electric field for two particles of charge E at distance L apart is E times L. And the energy needed to create a pair is 2m. I'm using units where c squared is 1, right? So now, so this is energy conservation. And now we look at the probability that a pair is produced. And it's e to the minus, in this case, d over lambda, where lambda is the quantum wavelength of this electron, right? So it's h bar over m. So the probability for pair production is e to the minus 2m squared over e. I just substitute. And in fact, Schwinger calculated more precisely the rate, so the probability per unit time, per unit volume for pair production, and he found that is E squared e to the minus pi m squared divided by E. Okay, so the prefactor E squared is just because of unit. Force has, in the units that I'm using, units of 1 over length squared, and we need 1 over length to the 4. So this is what it is. Now, yes?
What is D? Little d?
Sorry, L. D is the distance. Thank you.
Is there any way to kind of intuitively understand why the particle operation is exponential?
Is?
What the origin of this exponent, is it like clear?
Yes, because in this case, it's like tunneling or anything, something that is classically forbidden and occurs quantum mechanically. It's essentially exponential of the action divided by the unit of action. In this case, if you work out the units, then this is what you find. So now we can repeat this heuristic calculation for pair production in a gravitational field. Okay? And the way we do it is we convert the electric force to the gravitational force. So in this case, G, m black hole, divided by r square. Of course, this r will be roughly the Schwarzschild radius square. And then I have to multiply it by the particle energy rather than the mass. So this is, because we are dealing with the general relativity, it responds to energy and not just to mass. So this is roughly E divided by the Schwarzschild radius, because Gm is the Schwarzschild radius, and this is the Schwarzschild radius square, so I get E over Rs. And therefore, the gravitational pair production rate can read off here is epsilon square divided by Rs square, e to the minus pi epsilon square divided by epsilon over Rs. And this is equal to epsilon square over Rs square times e to the minus pi Rs e. Okay? And in this case, we find that the maximal rate of pair production, I can take a derivative with respect to E and find this way the maximum of the rate. And I find that it happens when E is about 1 over Rs, which is essentially the Hawking temperature. So at that point, the pair production rate is about T Hawking to the 4. So the picture that we find is a very simple picture, that every time that is the Hawking time, so that's time that corresponds to the energy of the Hawking temperature, a Hawking particle, a Hawking pair, or a pair of particle and antiparticles are produced with wavelengths that is roughly the Hawking temperature, or roughly the size of the black hole. One of them is going out to infinity, and one is falling into the black hole. And this is the heuristic picture of the P's and the Q's. The P's are the members, the positive energy members that go out to infinity, and the Q's are the negative energy member of the pair that falls into the black hole. Okay? Yes?
Pair production, does it only happen on the Schwarzschild radius or also in other places? Is it certain smaller probability?
In this case, of course, that you see that if you're in a region where the gravitational field is very small, the rate of the pair production is much smaller. So it becomes exponentially negligible compared to the rate that occurs near the horizon. Okay, so the point about the horizon is that their gravity is strong, and therefore you get pair production with essentially strengths of unity. So now this is all fine, but it still doesn't help us do calculations with the Q's. So what Hawking did is he used this picture to try and motivate the choice for the Q's. And well, the way he described it is that the horizon states, the Q's, will be chosen so that some of them describe those negative energy particles that the stationary observer considered to exist inside the black hole. Were you able to follow the logic? No, because, and this is the message, right? So you should take all of that with a grain of salt. The outgoing particles are fine. We were able to calculate them, understand what they are. This is a heuristic picture that should be treated with some caution. But nevertheless, let's go through the calculation that he did so that we have something more concrete. Yes?
In let's say, flat space, pair production is decay of gravitons, because I can't really have negative energy particles. Both particles produced have to have positive energy.
Depending on what you mean by I can't really have. right?
no,
If I consider quantum field theory,
yeah,
then I have
they're
a,
offshore, but then they have to, it's for a limited time.
exactly.
But
So here they materialize,
exactly, so this isn't exactly like pair production of an electric field.
yes, why not?
Are these virtual particles?
They are modes of the field. So, okay, if that's what you mean, then you're right. So what happens is that you are creating these modes, and then in Hawking's picture, they actually graze the horizon for a very long time, and eventually the idea is that they materialize as actual particles. One of them, the one that is going out, and the one that is going down, which has negative energy, is swallowed by the black hole. The energy of the black hole is decreasing, and that's how it shrinks in size. Okay?
This can't actually, this, as it happens on the horizon, it doesn't happen here. The same process doesn't
It
happen.
happens with a very, very small probability. I still have some gravitational field here, and then of course they don't materialize.
They can never materialize here
Right.
because they can on the black hole.
Right, this is true.
So this is unique to the horizon.
Yes, but unique, but quite vague. So I wouldn't use the so as a pictorial concept, it's fine. But when you actually want to translate it into a more precise concept, you start to have a little bit of problems, and that's part of the reason why that people get confused about what happens near the horizon. They view these as real particles sometimes in their mind, which they are not, and so on. So the best thing is, if possible, to avoid this altogether, because as we were starting to say, defining the particles near the horizon is something that we cannot do, because we cannot separate cleanly positive and negative frequencies, right? So the whole concept of particles is unclear there, and as you were saying, then afterwards, the pair production, you have to differentiate between virtual particles and real particles, etc., etc. So there are layers of unclarity in this description. But nevertheless, so it's, on one side there are levels of unclarity, but it's a concept that when people discuss black hole physics, they use a lot. So that's why I wanted to mention it. And we need it for the firewall, because this is a central concept there. And in fact, when in the next lecture, what I would argue that the part of the issues that are associated, the unclarity that is associated with the firewall, is that the number of these modes, that the number density of the modes that exist near the horizon is much lower than the usual estimate that assumes that these modes stay forever near the horizon. Okay, so all of that is important. Very good. So now, to discuss, it turns out that to discuss the Qs, it's again something that shows so to discuss the Qs, it turns out that it's better to integrate out the shell and replace this space-time by the space-time of an eternal black hole with specific boundary conditions. And that's what Hawking did. So what he did is It's not a very nice picture, but it's topologically correct. So he extended, this is H minus, H plus, the singularity. Right, so again, I assume that you've seen the Kruskal extension of a black hole. And what he does, he changes the space-time with specific boundary conditions here on the past horizon, which did not exist in the original space-time of the collapsing shell. So instead of the P's and the Q's now, he goes to another set. Well, let me first. So he writes in this space-time the scalar field that we have in terms of additional in a different basis, F3 and F4. Plus their emission conjugates. Okay, so he defines the F3 and F4 are defined here. I'm not stating in detail what the choices are. You can go and look in Hawking's paper. So that's, again, the same paper that we are discussing, PRD 76, and you go to the description of the ingoing particles. And there, everything is the exact boundary conditions that you choose. And then he further goes from this, the basis F3, F4, and F1 to Y, W, and Z. And they are, I can draw them schematically like so. So the Z's are just ingoing particles from square minus. The Y's are outgoing particles from H minus, and they are like the P's, so they are the outgoing particles. And the W's are particles that emerge here and are always inside the future horizons, and they are the analog of the Q's. Okay? And so these are the W's. And what he does, he follows the same method that we use of ray tracing through the shell, but now he goes through, this is done through the horizon. And here, there is a singularity here, and you cross, and you get the logarithmic phase shifts, etc., etc. And then what he finds is that for this set of modes, he finds that their creation and annihilation operators are related in a specific way. Right? So this combination annihilates the inflowing vacuum, the zero minus vacuum, and then for the Z, so the choice is that there are no incoming particles from infinity. And what you see here is that when a Y particle is created, a W particle is annihilated with some specific ratio. Note here that this specific ratio is e to the minus a half beta omega. So this you should recognize, right? You remember where encounter this combination of this combination, e to the minus a half beta e? Thermofield double, okay. So you see, this relationship tells you that particles are produced in pairs, right? A particle of positive a W is created, a Y is created, and a W is annihilated. It goes down to the hole. So this is the more precise manifestations of the pair production picture. With the caveat that the definition of particles is not that precise. And then this is already a hint that the state that is created is a thermofield double. So in this case, I'm not showing it, but Hawking actually showed it, that the state that is created is a thermofield double state that we have seen before. So the plus and the minus now replace the 1 and 2 that we had in the thermofield double. And in this case, you see that if we trace over the negative energy ingoing particles, we get a thermal state, which is exactly the outgoing particles that we encountered before. Okay? So this fits the previous calculation. Very well. Yes, sure.
In your Andrews diagram,
Thank you.
how this double line? I'm not really familiar with that notation.
This double line, no, it's just a double line that it's my graphical disability that I couldn't draw exactly, so it doesn't mean anything. But let me, since you asked me before, it's still not time for that. Okay. Yes, thank you. Okay, very well. Additional questions? No. Very good. So no significance, it's just very good. Good, so now we can go back to the firewall problem and state it. So let me do it there so that I can bring it up. Okay, so now we can state the firewall problem. The firewall problem is so let me say it and then I will write it. So the point is that we've seen in the page model that initially the outgoing radiation is coming out in approximately a thermal state. And then after the page time, it starts to purify. Okay? So the firewall problem is the statement that when the radiation starts to purify, the near horizon state cannot be a thermofield double state. It has to be a state that deviates significantly from the thermophile double state. This is more or less obvious, should be obvious by now, right? Because if the near horizon state is a thermophile double and I trace the ingoing particles, I get a thermal state. But when the radiation starts to purify, it starts to deviate from a thermal state. So it cannot be a thermophile double. This was, already known from the get-go, because everybody knew that only the Harter-Hawking vacuum, which is essentially this, is the one that has regular energy momentum tensor near the horizon. And this is stated everywhere. And so what this means is that if the state is not the Harter-Hawking vacuum, the energy momentum tensor is divergent. So this is not quite the same statement, because here there is a quantification of how much the deviation from a thermophile double state should be, and this is what I would like to show. So let me write it down. So the firewall problem is when the outgoing radiation starts to purify, the state of the pairs near the horizon has to deviate substantially from a TFD state, and so it has to deviate substantially from the zero minus state, and so you have a highly excited state near the horizon. And if this is so, if this is actually true, then this means that the equivalence principle has been broken, right? Because if I have significant energy density near the horizon, an infalling observer is able to feel it. And so the equivalence principle is broken. Okay, so this is what we were discussing initially, that when we try to keep the equivalence principle, try to keep GR, we break unitarity, and when we try to we keep unitarity, we break the equivalence principle. Okay, so let's see how this works. And to see that, we need a new technical tool called strong subadditivity that relates to three-partite Hilbert spaces. We learned the previous lecture about bipartite Hilbert spaces, spaces that are divided into two. And now we have to learn about Hilbert spaces that are divided into three parts. And the three parts in this case will be the outgoing radiation, the positive energy partners, and the negative energy partners. Okay? So we have to establish this the firewall problem, we need to understand what strong subadditivity is. And now instead of 2, we have 3 systems. In the AMPS paper, where they coined the firewall term, although Itzhaki in '96 already presented that problem, and then Matur and Brustein in 2009, but they didn't have the copywriting skills of naming this a firewall. So in the AMPS paper, the A is the early radiation. So this is the radiation that was emitted before the page time. And is already far from the black hole. Okay? B is the late radiation. So this one is after the page time. And C are the ingoing, so they are the ingoing partners of B. Okay? So the radiation that is already far from the black hole, the late radiation, and the ingoing partners of the late radiation. Is this clear? Okay, now Matur, in his version, so that's AMPS, and Matur actually used the same for A, and then or in this case it's slightly different. So it's the first N Hawking particles that were emitted, or outgoing part. B is the next emitted Hawking mode, and then C is that partner of that mode. But let me phrase it in terms of the amps. So yes. So they're outgoing mode. So the B's are the outgoing mode, and the C are the ingoing partner. Okay, so the strong subadditivity says that SABC plus SB is smaller or equal than SAB plus SBC, or equivalently that SA plus SC is less equal than SAB plus SBC. And so this I called 1, this I called 2, and you go from 1 to 2 by assuming a purifier D. Of the ABC system. Okay, so look at 2. focus your attention on 2 and look at the ABC box. So what is it saying? Is that SA, which is the reduced entropy of the A system. And then I add the reduced entropy of the C system. Before that, we were looking at just 2. So one was equal to the other. And now, but now it's not, is less equal than the sum of SAB. So if I just trace over C, plus SBC. So if I just trace over A. So you see B is the joint system here. Now, subadditivity is a statement about 2, which doesn't hold in quantum mechanics, right? So now this looks quite mysterious, but you actually can do a problem that is a little bit harder, but there is a paper that actually shows that. Quite recent, as you can see. It's a quantum pH paper. And again, in the spirit of my message from yesterday that the Rényi entropy is much better than the von Neumann entropy, if you look at the Rényi entropy, and you look at the Rényi entropy of Gaussian states, so essentially free fields, you find out that this result is just a statement about determinants of matrices. There's a big matrix, and these quantities are just determinants of submatrices, and this relationship is just followed from the so-called Hadamard inequality that is telling you that determinants of submatrices cannot be larger than, that the subdeterminants are the best way that they can behave is that if products of subdeterminants are giving you the full determinant, and they can only be small. So some obvious properties of eigenvalues of matrices. Okay, so that's really the origin, but I will not do this problem now. So it's basically some properties of determinants of submatrices, eigenvalues of submatrices. And so in this case, you see, let me erase this. So let's use this 2, so SA plus SC needs to be less equal than SAB plus SBC. So let's see what this means here. So SAB means that if I consider the entropy of the early and late radiation. So after the page time, you see the entropy, if I combine late radiation with the early radiation, the entropy decreases because it has started to purify, right? So this means that SAB, so after the page time, should be less than SA, because SA is the entropy of the radiation, and if it continues to grow, the radiation will never purify. So the idea is that the additional Hawking particles that join the initial ones reduce the entropy of the outgoing radiation until they purify at the end. So this is this, right? SBC, so If the near horizon state is approximately a thermophile double, this means that the entropy SBC is approximately 0 because it's a pure state. Okay? So if we now write it SA minus SAB plus SC, right, is less equal than 0. This is right negative, but this is roughly thermal, we know, because it's the trace over the thermophile double state, and so we get a contradiction. Right? But again, we don't really need this type of estimate. We know that if the state near the horizon is a thermophile double, and we trace over part of it, we get roughly thermal radiation. So we know that if we want the outgoing state to be different from thermal, this state near horizon needs to deviate from a thermal state. And here, this quantified by how much, right? Because we can use the page estimates and see that they deviate by order 1 per Hawking particle. So this is the firewall problem. Now, you can ask, what happens if this is true? What happens to somebody that falls into the horizon? And there are different issues, different ways of thinking, but for example, Itzhaki in '96 suggested that the Hawking particles, the W's and the Y's that are being emitted, kick the observer, and so kick the infalling body, and so it gets kicked all the time further and further until the black hole evaporates and they never enter the horizon. Okay, so from this point of view, the Penrose diagram of this type of picture would be that of a Minkowski space, because you would never have the insight. So it's in a way similar to the Penrose diagram of the infalling shell. Right? And that's, so, well, let me leave it at that. Any questions about this? Somebody knows how to resolve this, maybe? If not, I will tell you. Okay, very well. So I think now we have the two sides of the problem set up. If we keep the principles of general relativity, we're in problems with the principles of quantum mechanics. If we keep the principles of quantum mechanics, we are apparently in trouble with the principles of general relativity. So now the question is what to do. And this marks the start of my fourth lecture. Yes?
Is it not necessary to make any mention about the entangled nature of the particles, or does the entropy argument take care of that?
They are this S is the entanglement entropy.
Yes, okay. I said
Yes.
yes, that's right.
Yes. That's why I denoted it as. So when I said entropy, or this means the entanglement entropy, because in this case, you see the whole system, I think about it as a pure state. So it has no entropy, and the only entropy comes because I trace over part of the system and record that entropy of entanglement. Okay? So, yes. Very well. So now I can tell you what I consider as the essential ingredient in the resolution. In fact, you already heard it from Giyad Valley yesterday if you were here. And the main idea, this we will discuss in detail tomorrow, is, so lecture 4. The black hole as a quantum state. So I'm proposing, or I'm claiming, that the reason that we find these issues with the black hole is not because general relativity is incorrect or quantum mechanics is incorrect, but because we use an approximation. We treat the black hole with an approximation that is too crude. We need to refine a little bit our treatment of the black hole, and then many of the issues that we've encountered here will go away. So let me give you an example. Suppose that you had a big atom and it was decaying and emitting photons, okay? And now you neglect completely the fact that the atom, of course, the quantum wavelength of the atom is much smaller than the quantum wavelengths of the emitted particles. So the emitted particles are much more quantum than the big atom. But if you neglect completely the quantum nature of the atom and you were trying to follow the emitted photons, the phase information in the emitted photons will go away, right? You would get the impression that something is wrong with quantum mechanics, but the only thing that you did wrong is that you actually use an approximation which was a little bit too crude. So the idea is very similar here. And the first question that we need to ask is, how quantum is the black hole? So we need So in this case, let's use the standard measure of quantumness of objects. We look at their quantum wavelengths. Of course, this number is extremely small, right, for a macroscopic black hole. But nevertheless, it's non-vanishing. Some small number. And then the size of the black hole, so this is the quantum wavelengths. And this is the size, the geometric size of the black hole. And a measure of quantumness is lambda BH. I actually divide it by 2 pi divided by Rs. But if I wanted to find out how quantum an object is. I would look at their quantum wavelengths and I would compare it to some classical size that they have. Now, this is equal to h bar over 2 pi mbh rs. And you remember that rs, the Schwarzschild radius, is 2g Newton m black hole. So this actually comes out to be h bar g Newton divided by pi rs square, which is also L Planck square divided by rs square. Since you've been to Giastok yesterday, you know what L Planck is. And hopefully you know it before that, right? Pi. And this is 1 over S black hole. Okay? So we see here, now this of course for macroscopic black hole, it's a huge number. The entropy of a black hole the size of the sun is about 10 to the 76. So this number is very small. Now it's a dimensionless number, so I can compare it to 1 and say that it's very small. So it's extremely, a black hole is extremely classical. But nevertheless, it's not strictly classical. And the approximation that we have been using when doing the Hawking calculation, which is quantum field in curved space-time, we describe the black hole as quantum, a classical geometry, a strictly classical geometry. And in this case, QFT in, sorry. So let me define what the parameter CBH, that is 1 over SBH, which measures, it's essentially a dimensionless H bar, right? H bar has dimensions, right? So dimensions of a angular momentum, so it's momentum times length. So I can't take H bar to 0. I have to look at the dimensionless H bar, which is a number that measures how quantum an object is, right? So in this case, the CBH, 1 over SBH, is a dimensionless H bar. So the dimensionless H bar, and when we did the Hawking calculation, we actually set this CBH to 0 because we used a strictly classical geometry. And so this means that we have taken the mass of the black hole to infinity and g Newton to 0, such that 2 m black hole times g Newton is Rs is finite. So this is exactly the limit that Kia was discussing at the end of this talk. Right? And now, we can discuss what so the issue that we need to understand is by how much is the Hawking calculation change if we keep H bar, CBH, finite and repeat the calculation. Okay? And this we will actually do a calculation like that next time, but I want to explain first in a little bit more precisely what do I mean by the black hole as a quantum state. So let's say we look at a state where M is matter, M stands for matter, right? And I'm interested in finding out some expectation values in the state of the black hole and the matter. So for example, one such operator would be the expectation value of B dagger B, the number operator of the outgoing radiation that we were calculating before, okay? So according to the rules of quantum mechanics, what we need to do is evaluate this expectation value when we would like to calculate the expectation value of the operator. But when we apply the rules of quantum fields in curved space-time, we actually calculate. So what we do is we calculate a different expectation value where GC stands for a classical metric. Right? So when we did the Hawkings calculation, we fixed the background metric to be some GC. In our case, it was the Schwarzschild metric. And we calculated an expectation value of matter operator, let's say B dagger B, in that fixed background. Right? So that's what we did. But what we really need to do is calculate this expectation value. Now, there shouldn't be that much of a difference between them, but there is some. And that difference is based on many calculations, as you will see tomorrow, is that we find that in general, there are H-bar corrections, so dimensionless H-bar corrections to the pure, strictly classical calculation. Now this, if you know quantum mechanics, it shouldn't surprise you, right? When you do some quantum calculations, the first corrections come at order H-bar. But from the point of view of quantum fields in curved space-time, this is a huge correction. Because remember that Hawking argued correctly that the back reaction effects go like exponential. E to the minus SBH, right? So these type of quantum corrections, despite the fact that they're very small, they are huge compared to the back reaction corrections that Hawking thought that are the leading corrections. So from the point of view of the Hawking calculation, these type of corrections are very large and non-perturbative, because to create such a big quantum effect, you need many, many particles, the back reaction from many, many particles. So this is, in fact, this effect is the inverse of the back reaction. Back reaction is usually when the quantum fluctuations of the source back react on the metric. But here, these are quantum fluctuations of the metric or the background that affect the expectation values of matter operators. And now, typically, this is very small. So it shouldn't make that much of a difference in general. But if for some reason this classical expectation value, so the one that you get, vanishes, for example, when Hawking found that the off-diagonal elements in the density matrix vanish up to exponentially small corrections, and there is a source of corrections, quantum corrections, that is much larger, then these corrections become the leading corrections to the zero. And then the question is whether the zero is really a zero, or should we consider them and see what their effect is. And in fact, the conclusion is that these effects, or despite the fact that they're small, they actually accumulate because they are coherent, and they lead to purification of the radiation density matrix, similar to the one in page. Okay, so, and this is what I will show in the next time. In the meantime, let me end with a suggestion about something that you should think about. And let's try to think about the situation where the geometry is quantum. Okay? And imagine that you have a source, some source, we will discuss it in more detail next time. Suppose that you have some spherical mass and you put it in a superposition state. You can do it, right? Now, how would a test particle in this type of background move? Any idea? If it were just a single classical mass, how would the test particle move? This you should know. Very good. On geodesic, right? Of course. But now what happens if I have a state which is a superposition? Okay. Try to think about that. It's something that we usually don't encounter, but in fact it's possible to set up in the lab a situation where macroscopic masses are in a superposition state, and then it's possible to test this idea experimentally. So this is showing, again, as Gia was discussing yesterday, that when we talk about quantum gravity, we don't necessarily need to think about Planck scale physics. Gravity is quantum also in our world. We don't usually think about it, but to understand some of the issues that are associated with black holes, we have to start to think about it. Okay, thank you.
What about a different solution to the Firewall paradox, where you just have...
I didn't even said one. I didn't suggest one, so I guess.
Different
Yeah.
direction for a solution where there is a physical object on the horizon. Because I think, is it true that the equivalence principle would only be broken if there is some special point in space?
No. So for that, we need to be a little bit more precise about the definition of the equivalence principle, right? So the equivalence principle states that if we do only gravitational experiments, so there are no other forces, and we look at a small enough region of space, gravitation and acceleration should be equivalent. Now here, if you had a real physical wall on the horizon, this will not be the case, because in this case, somebody that falls in will actually hit that wall. So they will be able to tell the difference between acceleration and gravitation.
But it's true about this wall too.
This wall doesn't break the equivalence principle because it uses forces that are not gravitational. See, the equivalence principle is not saying that you cannot have a difference between gravitation and acceleration. It only says that this cannot happen if you have just gravitational forces, just gravitational interaction, and also it needs to be in a small enough region of space. So, space-time actually. So for example, even if you use just gravitational forces, so let's say I take some pendulum in the space shuttle, and I wait long enough, I will be able to tell the difference between acceleration and gravitation, because in this case, I'm not violating the equivalence principle because I'm looking at a long enough region of space-time. So if this wall was purely built of purely gravitational interaction, then it would violate the equivalent principle. But if it is really dominated by, in this case, electromagnetic interaction, then the equivalence principle is not applicable, because the conditions are not applicable. So, you agree?
If someone hits the wall, he is not freely falling.
But not freely falling means that this wall is dominated by other interactions. In this case, the equivalence principle is not committed about what happens, right? So it's okay. Same, by the way, in this case, if you have other scales in the problem. So if you consider a quantum version of that and you have some quantum wavelengths, the scale of the experiments that you do has to be smaller than the quantum wavelength. So whenever you have a scale that is not originating from gravitational interactions, you have to do the experiment in a smaller region of space-time than this other scale for the equivalence principle to be valid. Yes?
Firewall is generated by these W and V particles, which hit the observer, right? And they are not gravitational.
Everything here is gravitational interaction. So you think about them as these as gravitons, right? So
C are gravitons. B and C are
you can think about them as gravitons. There are also other particles are produced, but in this case, it's just gravitational interactions that are producing this effect.
made of gravitons, right?
Well, in this case, you can have other particles, but the infalling person can be insensitive to other interactions. So I can think about a probe that is sensitive only to gravitational interaction, and nevertheless, if you have a firewall, so in that case, if it's burned, then the equivalence principle is actually violated. Yes?
Are these, so with if you're assuming there's high energy modes at the horizon, are these transplanted or?
Well, you're opening a can of worms. So, I should probably explain what Transplanckians are. It's actually a red herring. All this Transplanckian stuff is a red herring that I'm very sorry it continues on to propagate. And no. So in this case, the field theory that I'm considering in the background of this black hole has a cutoff. And that cutoff has to be, for consistency of treatment, sub-Planckian. And the particles that you're producing here are at most at the cutoff scale of the field theory. So trans-Planckian, out.
But then there's no explanation how they originate. I mean, since they just pop up with that.
Well, in this case, you sort of understand. The strong gravitational field is creating them. And from a point of view of an observer on infinity, they are created at all allowed energies. So they see a high energy density region, and they fall and get burned. That's the idea of the firewall. Okay? Additional questions?